Hello, everybody. My name is Laura Cadonati from Georgia Tech. I am the new chair of the new division in gravitation, and I want to thank APS for sponsoring this special lunch session today, where the LIGO results will be presented. Our first speaker today is Professor Dave Reitze, who's the executive director of the LIGO laboratory at Caltech, a professor of physics at the University of Florida. He has worked extensively in the area of gravitational wave detection over the past 20 years, and between 2007 and 2011, he was a spokesperson for the LIGO Scientific Collaboration. He's a fellow of both the American Physical Society and the Optical Society of America. Please welcome Professor Reitze as he tells us about our discovery.
Thank you very much. Can people hear me? Yes? Here, I'll move this up a little bit. Thank you very much, Laura. It's really a great pleasure and an honor to be here and tell you about what we all in LIGO think is really just a phenomenal discovery, the discovery of black holes through gravitational waves. So this is the first of two talks. I'm going to be telling you a little bit about the detector and a little bit about the event that we saw, the black holes. And then Vassiliki Kalogera is going to talk to you a little bit about how we know about these black holes and what it says about the astrophysical implications. So let me get started. I suspect most of you in here are very familiar with general relativity, but for the few of you that aren't, this is a one-slide primer in general relativity. We'll go through it very quickly. There will be a test at the end of my talk. General relativity is a beautiful mathematical theory that was really developed by Einstein 100 years ago. And it basically says that matter and energy are linked with space and time. And that's what that Einstein field equation does at the top left-hand corner. It basically says that when I put matter in a flat space-time, it warps the space-time. And the warpage depends, the curvature of the space-time depends on the amount of mass or matter that I put in. And then it also says that that warpage tells the matter how to move. Matter moves on geodesics. All right, so that's one slide or one statement on general relativity. If you want to know more, take a course. I'm going to then make some assumptions. I'm going to assume that there's no matter in the universe. All right, so T mu nu, that tensor quantity on the right-hand side of the equation, is 0. And I'm also going to assume that the perturbation is flat. In other words, space-time is almost Minkowskian. All right, and the perturbation, that little perturbation, h mu nu, is just a perturbation on the geometry of space-time. And that goes into the left-hand side of the equation. If you put those two things together, you do about a page of mathematical algebra, you derive a wave equation. And everybody, I hope, is familiar with the wave equation. The solution to that wave equation, as we all learned from E&M, are propagating plane waves that propagate out as a function of time, exponential waves. And the amplitude of those plane waves is that quantity h mu nu. Now, the problem here that we face, and all gravity experiments face this, gravity is a really, really weak force compared to all the other forces. And the coupling constant between matter and space is that quantity 8 pi g over c to the 4th. And that number is about 10 to the minus 43. So that tells you that you really have to put a lot of matter into space to warp it appreciably. Okay? So it also will tell us about how hard it is going to be to measure gravitational waves. So physically, what is that quantity h? Physically, it's a strain. It's a delta L over L, a change in length per unit length, which says if you want to measure strains from astrophysical objects such as colliding black holes, you need to make a device that measures delta L as small as possible. You want to make those displacement measurements as small as possible, and that's a real challenge. You also want to make a measurement over a long baseline, over a baseline as long as possible. And for LIGO, that's about 4 kilometers. If I then calculate, using general relativity, what that h mu nu is for a given source, it turns out that unlike electromagnetic radiation, all right, the h mu nu is sourced, the gravitational waves are sourced by the quadrupole mass moments. So they're dipole forbidden. So the first leading term is quadrupole. There's that factor g over c to the 4th again. The I double dot is the second derivative of the quadrupole mass moment. The 1 over r is the distance from the source to the detector. Okay, Now, gravitational waves come in two polarizations, and they're schematically showing as those oscillating fields there. What happens as a gravitational wave passes through you is it stretches time or stretches space in one direction and compresses it in the other direction. And if you do this calculation, what is h mu nu for a system, for example, of two binary neutron stars that are orbiting around one another? The answer is h is a really small number. It's 10 to the minus 21. So that's what makes this business so darn challenging, that we have to make these measurements like this. All right, why are gravitational waves interesting? Well, they're interesting because they're a prediction of general relativity, and the fact that we directly detected them and measured their amplitude and phase tells us once again that general relativity is right, and I'll show you that later. But it also answers a lot of questions, other questions. First of all, questions about black holes. Are black holes truly bald? In other words, are they only described by their mass and angular momentum? And astrophysics, how many black holes are there in the universe, low mass black holes? Do compact binary black hole mergers lead to gamma ray bursts? If I have two neutron stars and I slam them together, does that produce a gamma ray burst? We know that gamma ray bursts exist. We don't know where they come from because we haven't yet correlated it with a gravitational wave signal. So there are a number of really exciting questions that gravitational waves, interferometers such as LIGO and Virgo will be able to measure and answer, we hope, over the next few years. All right, so how do we do it? How do we actually measure a gravitational wave? And this is a one slide, again, this is a primer on precision interferometry. Right now, Peter Salson and I are in the process of editing a book where a number of the leaders in gravitational wave detectors have contributed chapters for us. That book hopefully will come out later this year. If you want to learn more, I urge you, plugging this book, to read that. But this is the one slide synopsis of that book. Basically, we use enhanced Michelson interferometry. So that picture that you see there is what the LIGO detector actually looks like. You'll recognize there's a laser. You'll recognize there's a beam splitter. That's where the beams separate. You'll recognize there are mirrors at the end. Those are called end test masses. All right, but then there are some enhancements that we put in. We put in input test mass mirrors, which makes Fabry-Perot arm cavities, which leads basically to the interferometer thinks it's much longer than it is, so the gravitational wave interacts with it over a longer time period. We also use something called power recycling or photon recycling, where the light that doesn't get to the dark port of the beam splitter, that's that conic-looking thing there called the photodiode, all right, gets recycled in, and that helps us enhance the sensitivity by overcoming shot noise. And then there's something called signal recycling, that last little mirror that sits by the photodiode. All right, that allows us actually to tune the sensitivity of the interferometer, and it provides more sensitivity. So all these really optical tricks are absolutely necessary to make a measurement of this order of 10 to the minus 21. And a gravitational wave, there's a gravitational wave in the picture that's sort of coming downward. All right, that what it will do is it will stretch one arm of the interferometer, compress the other arm, and over a full cycle, that process will repeat itself. Now, that picture that you see there on the bottom, the strain that you see there is about 0.2, so it's actually greatly exaggerated by about 10 to the 21. All right, so we're trying to detect things that are much, much tinier than that. The other thing I'll say is that because of the nature of gravitational waves, the interferometer is sensitive to their amplitude, which is nice, which means we can see out a distance. It's not a 1 over r squared effect, it's a 1 over r effect. So that's all very nice. All right, let me tell you a little bit about LIGO. LIGO is 2 interferometers. We have one operating in Hanford, Washington, one operating in Livingston, Louisiana. They are identical in what they look like. The interferometer configurations are identical. They're separated by about 10 milliseconds light travel time. We are funded by the National Science Foundation, and the National Science Foundation has been supporting this effort for really over 25 years. And in fact, even before LIGO existed, the experiments on trying to understand how you would make a gravitational wave detector 15 years before that. So we're grateful for that. The LIGO laboratory at Caltech and MIT is the organization that manages the observatories and operates the observatories. There's a much larger group of people, of which people in the LIGO laboratory and many other institutions are involved in. That's called the LIGO Scientific Collaboration. There's about 1,000 scientists in the LIGO Scientific Collaboration, all of whom contribute in meaningful ways to the science that we're going to get out. This is big science. We need all these people. And I'll point out that many of them are actually here in the audience, so you might be able to interact and meet with them. And then we also work with the Virgo Collaboration, which is a group of scientists in Italy that operate another detector. All right, so this is just a picture of one of the observatories, so you get a sense of scale. That big building that you see in the bottom right is the corner station where the laser is. You can see the arms going out in both directions. They're 4 kilometers long. If I were to show you the Louisiana site, it would look much like this, except for it would look a lot greener. Hanford is in a desert. Livingston is in a swamp. So, all right. More on the interferometer, and again, I really can't go into great detail simply because I don't have time, but there are several key pieces of this interferometer that allow you to get to that sensitivity. And maybe what I'll do here is I have a pointer. So I'll start, yes. So we start with a laser. This laser was developed by the Albert Einstein Institute, supplied by the Max Planck Society, and it provides up to 200 watts of light. That light comes out here and goes through something called the input optics, which is basically a very sophisticated filtering system that prepares the light to go into the interferometer. The input optics is shown here. Here are the key core components of the interferometer. You can see there's a seismic isolation system that the mirrors rest on. The mirrors are also suspended, and these are very, very sophisticated suspensions. They allow us to reduce the seismic noise that the Earth naturally sort of generates because of normal motion by about a factor of 1 trillion. There are auxiliary arm locking systems, so we have the ability to control each of the interferometer arms and lock them up independently. And this is very important. It saves us time when we're operating. There's something called an output mode cleaner. The output mode cleaner was supplied by Australia, the Australian Research Council, and a group at ANU, which basically provides the final level of filtering the light. And then there are 2 photodiodes, and that's where the gravitational wave is seen. And I should point out, by the way, that the suspensions, which are really key to what we're doing, were supplied by the University of Glasgow and Birmingham. So it's a real international detector that we've built here. All right. But in fact, precision interferometry is about understanding and measuring noises. And this is where it gets really challenging. So this picture that I show you, on the x-axis is the frequency spectrum. So in some sense, this is the bandwidth of our detector. This is the frequency range over which LIGO can see it. On the y-axis is strain, that quantity h, and amplitude spectral density, so in 1/√Hz. And you can see, and this is a very, very simplistic view of the noises that we have to face, but you can see in different regions, there are different things that we have to worry about. So at low frequency, we're dominated by that seismic noise, which is brown, that brown curve there. And then there's also something called gravity gradient noise, the fact that things move, and when they move, they generate dynamic gravity, and that can couple to the test masses. Then in the mid-band, we're limited by that red curve, which is coding thermal noise. And I won't go into great detail. I will suffice it to say that it's a real challenge for us. The mirrors themselves actually vibrate because they're at a finite temperature, and the coatings actually are the thing that vibrate the most and cause us the most noise in that band. And then the purple curve, all right, is quantum noise. And there are 2 flavors to quantum noise. One of the flavors has to do with basically the time of arrival of the photons. Because the photon's a quantum field, all right, there are fluctuations with that field, and the time of arrival is an equivalent to a change of phase, if you will. So we have to worry about that. You can beat that by raising your laser power. There are other ways to beat it too, as I'll talk about later. At the corollary of that at low frequencies is radiation pressure. So the photons carry momentum, all right? They exert a force, basically the power of the laser over the speed of light, and the fluctuations of the power translate into a fluctuating force. So that dominates at low frequency. And then there are a few other curves. There's basically the vacuum system. We have to put everything in a vacuum system. So there are a number of things that you have to do to make a good detector. Suffice it to say, if you design your instrument right, there are also technical noises, which I'm not going to talk about. If you design your instrument right, you can beat all those noises, and this was in fact the sensitivity that we achieved during the first LIGO run, which detected the gravitational wave. So now let me switch to that. So the gravitational wave that we're going to talk about came in on September 14th, 2015. So really almost 100 years after Einstein postulated his theory of general relativity. So the timing couldn't have been better here. So before, when I used to give talks about LIGO, people would go, "What have you discovered?" And I would say, "Nothing," and I'd have to show this slide. But then I would say, but wait, we've done a lot of good science. So up until we discovered this gravitational wave, we've published about 100 papers. All right, and they're just going to roll by there for a second. And even though there was no discovery, there was actually a lot of good science in those papers. For example, the last one was in Nature that came out in 2009 on a limit on the stochastic gravitational wave background. Well, that's good, but really that's not satisfying. You want to detect something. So fortunately, Nature gave us this. All right, and this is a rendering, if you will, by the Simulating Extreme Space-Time Collaboration of an event that we detected on September 14th. It's two black holes merging together. All right, it's give or take a few hundred million years, and the reason why that is because we can't get the parameters quite right. Anyway, this is a remarkable discovery for a lot of reasons. So let me show you the data. This is figure 1 of our paper. If you haven't read the paper, I would urge you to do so. It's really a very well-written paper. It's very clear and easy to understand. I won't go through all of the plots here. I'll focus on the top one because I think that's the interesting one. So this is the raw data, and there are two panels. One is from Hanford, one is from Livingston. The left panel is Hanford. That's the raw data. All right, there's a little bit of filtering. We filter below, we take everything below 30 hertz out. We take everything about 350 hertz out. But you can clearly see the oscillations. And those oscillations are pretty much exactly what you'd predict from general relativity. All right, you can look at the same data in Livingston, and we show it there, and it's overlapped in that left-hand plot. Now, we've done a little bit of manipulation. We've shifted the data by 7 milliseconds. That's because Livingston saw the signal first, a point which they never let Hanford forget. Livingston was the first one to see the signal. And you had to invert it just because of the orientations of the interferometers. But you can see right there, just in the raw data stream, that you've got a consistent signal. And then you can do some, you can subtract out the best fit templates, and that's what's shown in the second figure there, even using numerical relativity or something called EOBNR, even wavelet construction. And you can see that the data is very, very consistent with what you'd expect for colliding black holes. And there's a huge amount of information in that waveform, and I'll tell you that. Oh. I want to go back and do that again. What I'm going to do is play for you the sound that basically, if you take the signal from the photodiode, filter it a little bit, this is what you hear out of the photodiode. And at the end, you should hear this thump. Okay? If your ear is really good, you can hear it. The fact that you can actually hear that thump in the signal tells you how loud the signal is. It was really a very impressive signal for us. All right, talk about the source parameters. Vicky is going to go into a lot more detail here. The primary black hole was about 36 solar masses, again, give or take, maybe 5. Secondary mass, 29 solar masses. And that information all comes out of those two waveforms. So those two waveforms contain a tremendous amount of information that allow you, with some errors, to infer these things. The final black hole mass is 62 solar masses. The final black hole spin, that's basically the normalized spin parameters, about 0.7, 0.67. Not quite the optimal spin, but very close. The luminosity distance, the distance to the source, about 410 megaparsecs, 1.3 billion light years. The redshift, you can convert that to redshift, it's a little bit less than 0.10, 0.9. The other two things that are important, if you do the math, and you add up 29 and 36 and subtract 62, you'll get 3. And that's the amount of energy in solar masses that was radiated during the last 200 milliseconds of this event. So you can see that this is a tremendously energetic event. The peak luminosity of the event was about 3 times 10 to the 56 ergs per second. And to put that into comparison, that's basically if you take the entire average quiescent luminosity of the electromagnetic universe, this is about 50 times higher. All right, so I need to, let me finish up with this. I'll just say, or I'll keep moving here quickly because I'm going to run out of time. Are these black holes the black holes of general relativity? So that answers the first question I asked. And the answer is yes, to the level that we can measure them. All right, so these black holes, because there's noise on the data, we can't say with 100% confidence, but we can say with 96% confidence that these are the black holes of general relativity. Perhaps the most interesting thing to me is after we made this announcement, we got a lot of press. And the press was actually overwhelming, I think, for a number of us. But it became embedded in popular culture. And I won't read the Guardian comedy here, or cartoon here, because I don't really have time, but I'm just going to walk through a few things. So in fact, if you want to buy a dress that has the gravitational wave pattern on it, you can do that. And actually, I should point out that this Shinova company is really quite nice because it's run by somebody who's very interested in women in STEM. And so she pushes a lot of these, she designs a lot of these dresses. So I would urge you to go out and support this. I think my favorite is that apparently the city of New York believes that finding storage space is harder than finding gravitational waves. Because it says, scientists found gravitational waves in outer space. If only it were that easy to find an apartment in New York City with a walk-in. All right, I don't know what ad campaign came up with this, right? Very recently, this is a world champion 100-meter freestyler from Australia. And he's very interested in gravitational waves, so he put the gravitational wave waveform on his cap. All right, anyway, because I'm running out of time here, I'm going to wrap up pretty quickly. The data that we generated here, you can actually get. All right, we have something called the LIGO Open Science Center, and that allows people to download the data around the event, and you can play with it yourself. All right, what comes next? Well, there's a network of these detectors, and the two detectors that we're operating for the discovery were the two LIGO detectors, but there's also GEO 600, all right, which is a slightly smaller detector in Germany run by the GEO Collaboration. Two detectors under construction, one in Italy, Virgo, one in Japan, Kagra. They will be coming online, we hope, in the next Virgo this year, Kagra in a few years. And very recently, India decided to go forward with the gravitational wave detection project using the advanced LIGO detector design. So this would, in some sense, be the third leg of the LIGO network. And why is that important? That's important because, as I think Vicki will go into this a little more also, you can actually localize sources using multiple detectors. One detector is not very sensitive to the sky position of a source, but 3 detectors are, and 4 detectors even more. So this picture on the right, or on the left-hand side, is the localization for GW 150914. You can see that it's very poor because we only had 2 detectors. It should be a ring. It's a little bit better than that because we have some consistency checks that we put in, constraints. If you take that same event and ask yourself how well localized it would be using Virgo and LIGO and using Virgo and LIGO in India, and the answer, it gets a lot better. It goes from about 375 degrees in that picture, the blue plot there, to about 7.8 degrees. And that's really interesting because telescopes can really hone in on that, and it's hard for a telescope to hone in on these broad swaths. So the plan going forward is we'll keep improving our detectors, and we hope actually to implement upgrades using something called squeeze light, which allows us to get beyond the shot noise limit, and that will take us into 2021. Even beyond that, there are plans on the board and people's heads for building new detectors, and those new detectors will even go a factor of 3, maybe even a factor of 10 beyond LIGO, the current LIGO, and that will allow us to see basically every black hole in the universe that was ever formed in the universe. So there's really a very bright future here. I should point out that LIGO is only one part of the spectrum. It's the high-frequency part of the gravitational wave spectrum, so we've detected gravitational waves that have periods of milliseconds. Hopefully LISA will launch, which will have gravitational wave periods of hours, minutes to hours. That will see heavier mass black holes, intermediate mass black holes. Pulsar timing is another way that you can detect gravitational waves, and I'm very optimistic. I'm hopeful that they'll be making a detection. They're looking at supermassive black holes in the center of galaxies. Perhaps that'll happen over the course of the next couple of years. And then finally, a primordial gravitational wave background. That should happen soon, too. So it's really in a very exciting time, and I think I'll stop because I'm running out of time. I'll summarize my conclusions by saying it's been a really exciting couple of months, and the next few years should be very, very exciting for this field. I want to thank the LIGO Scientific Collaboration. That's all of the groups that really made meaningful contributions to this. The Virgo Collaboration, again, without them, we would not be able to do some of what we're doing here. And I'll point out that this meeting has a lot of good talks on gravitational waves, LIGO, and numerical relativity. So actually, unfortunately, you've missed about half of them. But there's still about half of them to go, and I urge you, if you're interested in this, to go and see some of these sessions. And I think with that, I'll close. Thank you very much.
Thank you, Dave. We have time for a few questions.
While all the excitement naturally is on the merging black holes and the potential for future observations of that, I'm interested also in the ability to detect the stochastic gravitational wave background. And as you pointed out, the first LIGO generation already placed some upper limits on it. But could you comment on the different challenge that places? You don't have a template to a waveform to fit. Could you comment on that?
Sure. So if you believe inflation, the amount of gravitational wave density, energy density that's in our band, this high frequency band, all right, is about 10 to the minus 18. And initial LIGO was sensitive to about 10 to the minus 5. Advanced LIGO maybe gets us to 10 to the minus 9. So if it's simple, slow roll inflation, we're not going to see it. We use cross correlation of the two detectors, standard techniques. There's lots of filtering that has to do to make the data clean, but that's the technique that we use. Now it's very possible, however, and I'm going to change your question a little bit, that in addition to the primordial gravitational wave background, which I think we would have a hard time seeing, there's also a stochastic background from the fact that there are lots of binary black holes that have merged, and all those gravitational waves are sort of incoherently still out there. And a paper that I think has come out or will just come out in PhysRev Letters by the LIGO Scientific Collaboration and Virgo Collaboration basically puts a limit about 10 to the minus 10, so we might actually be able to see that. I think to see the primordial background, you really need to do these experiments like Keck or BICEP, follow-ons to BICEP2 or space-based experiments like CMB pole.
I just want to point out an exception to what you said. Your statement about the level of the background is based upon the standard prescription for cosmological background from inflation into a radiation-dominated universe followed by a matter-dominated universe. But there are models of the background universe and even of the nature of dark matter, scalar field dark matter being one of them that I happen to be working on, in which the universe passes through a stiff phase, which is not radiation-like, and this serves to amplify the gravity wave background by orders of magnitude. So it may be more optimistic than you think.
I hope so, and that's why we look, by the way. Okay. So we're not ignoring that source.
Is there one more question? Okay, thank you. Thanks again, Dave. Our next talk will be delivered by the recipients of the 2016 Bethe Prize. The Hans Bethe Prize, jointly awarded by the APS Division of Astrophysics and the APS Division of Nuclear Physics, recognizes outstanding work in theory, experiments, or observation in the area of astrophysics, nuclear astrophysics, or closely related fields. This year's recipient is Professor Vassiliki Kalogera of Northwestern University, who's been honored for her key contribution to the study of electromagnetic and gravitational wave radiation from binary compact objects, including the now verified prediction that neutron-star mergers produce short gamma-ray bursts that will be found in all galaxy types. Professor Kalogera is Heaven Professor of Physics and Astronomy, Director of the Center for Interdisciplinary Exploration and Research in Astrophysics at Northwestern University, and a Fellow of the APS Division of Astrophysics. Please join me in congratulating our speaker, Professor Vassiliki Kalogera.
Thank you, Laura. Can you hear me? It's a double honor for me. It's a really great honor to have the opportunity to give this talk on behalf of the LIGO and Virgo collaborations. And it's even more daunting to be giving it in front of our spokeswoman, Gabby Gonzalez, who should be up here instead of me. I also want to thank the divisions of astrophysics and nuclear physics, not only for the selection, but also because they allowed me to combine the prize talk with this plenary talk. Normally, I was going to give a second talk later in the afternoon, and I'm happy I don't have to do it, to be honest. I need to note that the citation for the prize is really mostly focusing on neutron star binaries and their connection to gamma ray bursts. But with the opportunity of this LIGO discovery, I'll spend, of course, my time talking more about binary black holes. But I don't think Hans Bethe would mind that, as in his last few years, he was actually studying, mainly with Jerry Brown, black holes in binaries. So I'll get started with where Dave left off, and I'm going to tell you about the implications of the LIGO discovery, particularly in the context of testing GR and in the context of astrophysics. But in order, I'm missing the slide. Okay. But in order to do that, first I need to tell you the work we did after the detection was established within the data. And that work has to do with physically characterizing the signal and the source. And the way we do this, obviously I won't go into the details, but the way we do this is having waveform models for what we expect for a potential gravitational wave source, and then match filtering the data and finding the likelihood space distributed in a large number of parameters, depending on the waveform you're using, more than 10 dimensions. So tracking this likelihood complex space and finding the peak and then sampling from the peak and estimating the errors of the parameters involved. So we have done this in the collaborations with 2 different stochastic samplers, 2 different binary coalescence waveforms that have different assumptions about spins, and also a generic waveform that doesn't even make any assumptions about having a binary and having an in-spiral merger. And all these analyses give consistent results, which of course we were very eager to see and very happy to see. So let me get started with the masses. Dave mentioned them. I'm showing you here the, let me use the mouse, the banana, a truncated banana in the 2D plane of the 2 masses. The primary mass is at peaks at about 35 solar masses, and the secondary mass at about 30 solar masses. This translates then, allows us to derive, also using numerical relativity models, allows us to derive the properties of the final black hole that forms, with the peak being at about 62 solar masses, and the final spin at around 67% of the maximal spin. And that spin, we understand it right now, as far as we can tell from the signal, to be coming mainly from the conversion of the orbital angular momentum into the spin of the final black hole. Other parameters, we're very interested in black hole spins. For this particular signal, it is hard to place strong constraints on the spin. For the spin aligned with the orbital angular momentum axis, we can only set an upper limit, and that upper limit is quite tight, so small aligned spins is what are preferred. And then for the spin component in the plane of the binary, there we have a very hard time placing a strong constraint given the properties of this signal. Other parameters of interest, obviously the distance. You see the peak distribution, the peak of the probability distribution is at 400 megaparsecs for standard cosmology. This basically corresponds to a redshift of about 0.1. And we can also set some constraint on the orientation of the binary plane with respect to our detectors, with respect to our line of sight. And we can tell that probably this system was face off. So the orbital angular momentum is pointing roughly away from us. With all this work, we also extract with, again, very different methods, some very prompt, fast methods, some that take more time. We extract the sky location on the sky. That's this little banana that I remember when I first saw it. The first time I showed this to a public talk, somebody from the audience said, the sky is smiling at you. So this covers 600 square degrees. We'll come back to this later in the talk. It's obviously a large area on the sky. Despite this large area, we had communication agreements with a lot of more than, I think, 60 electromagnetic partners. So a lot of teams followed up this trigger well before it was publicly known in the X-rays, optical and infrared, and radio. And all teams reported upper limits, except there is a claim for a potential Fermi GBM gamma ray burst counterpart. Of course, this is unexpected because with 2 binary black holes and potentially no matter around, you wouldn't expect an electromagnetic signal. But of course, theory colleagues, especially in the astrophysics community, have been very productive immediately after the Fermi news to think of ways of getting an electromagnetic signal from a binary black hole, although the existence of the signal and its association with the gravitational wave discovery is still under debate. All right, so I will try to just give you a very quick flavor of how we tested GR. I will point out that we, as a collaboration, we worked on unmodeled tests of GR without assuming any particular alternative theory. And we did this in a few different ways. I will not describe all of the ways in detail, but the one thing I would like to point out is that this source is giving us the very first opportunity to test GR in the strong field regime. And the reason is that the 2 black holes at the very end of their life, before they merge, as they are sweeping through the LIGO band, they are reaching velocities that are almost about half of the speed of light. In comparison, our best tests are coming from the double pulsar that you probably have heard, and the velocity of the neutron stars in that system is at 10 to the minus 3 of the speed of light. So clearly we're in a strong field regime with this source. And as I said, we do different tests. Some tests have to do with removing what we think is the best signal from the numerical relativity analysis, and then looking at the residuals and finding that the residuals are basically perfectly consistent with our noise in the data. We also look at the signal in a way that you can separate before the merger and after the merger, not use strong field GR, estimate the properties of the final black hole, and then compare to what you are getting from the full analysis that accounts for general relativity in the strong field regime, and find that all of these are consistent. Again, hinting at clear consistency for general relativity. The third kind of test connects to the fact that we can expand the phase of the gravitational waveform as a function in the post-Newtonian way, as a function of V over C terms in different powers. And the coefficients of these terms, shown here, in general relativity are well known, and they depend on the masses and spins, etc. And we can evaluate these and then ask the question, using the signal, what is the upper limit you can set in terms of some kind of a deviation from what you expect from general relativity. And you do this term by term, looking at the coefficient. And what you can see here as a function of different post-Newtonian terms, we are plotting these upper limits for this deviation from GR. In blue is the results we have from the double pulsar, and in yellow is the results from the gravitational wave source. And you can see that already at half PN order, we are improving these upper limits, and for the first time ever, we're actually probing and quantifying these upper limits at higher PN orders in a way that we cannot do it with a double pulsar. Okay, astrophysics now. I'll start with the main conclusions because I'm not sure I'll get to explain why we have reached these main conclusions through the slides. So, of course, the zeroth order implication for astrophysics is that binary black holes exist. We didn't know, I don't know if you fully realize that we only have experimental evidence from electromagnetic astronomy for double neutron stars. We have never observed a black hole neutron star binary or a binary black hole. So this is the very first evidence ever observationally that they exist, but of course they have been predicted in theoretical models for a long time. Now, the formation of this particular system requires an origin from a low metallicity environment. A conservative upper limit on the metallicity is half of solar, and that has to do with how massive the black holes are. Also, we find that this kind of massive binary black hole has been predicted to form in both isolated binaries, regular binaries, or through dynamical processes in dense stellar systems. Both of these formation channels can predict, depending on assumptions, rates that are comparable with what we extract from the event, and the low end of rate predictions for binary black holes is being excluded. So these are the top conclusions, so I'll try to justify each one of them, and we'll see where that takes us. Let me start with rates. So we have one source. You might say one source doesn't give you a rate. That's true. Although, I've worked for many, many years on getting rates from binary pulsars when we only had 2 before the double pulsar. And that's a daunting job with high uncertainties, but we can do it. So in LIGO, we have the one discovery, but we also have lower significant triggers. If you have read the paper, we discussed the next most significant trigger. And if you take that into account, then you can extract a rate. The rate turns out it is dominated by this second most significant trigger, given how rates work. But in any case, we have a constraint right now. It's rather broad, 2 to 400 in these units that probably don't make that much sense to you right now. 2 to 400 events per cubic gigaparsec per year. But in comparison, what theoretical predictions have given us over decades of studies is that you would either have no binary black hole mergers or all the way up to 1,000 events in these units. And clearly, with the discovery, with the LIGO discovery, we are excluding the low end of the rates. So our rates below about 1 in these units are excluded. All right, now let's go into more consideration of the black hole masses and the formation. Obviously, I said first binary black hole system, but the intriguing thing is that the black hole masses we observe and measure in this system, including the error bars, are well above 25 solar masses, and that regime is well above the black hole mass measurements we get from X-ray binaries, which is the only other way we have of measuring stellar mass black holes. So these heavy black holes imply something about the formation and the stars, the formation of the system and the stars that led to the black hole formation we see in the system. I will not describe these two plots in detail. They're a bit too complex, but I want to give you a very quick sense of them. If one looks at black hole, the maximum black hole you can form based on stellar models as a function of metallicity, then of course you want your curve to cross the measurement based on the LIGO discovery. Also, you can look at what is the black hole mass you can get from theory as a function of the initial stellar mass for different metallicities. If we combine these two together and we use the results from many different groups, on the left-hand side is a study from Belczynski et al. 2010, right-hand side, Spera et al. 2015. The conservative constraint is that metallicity must be subsolar in order to form massive black holes as we observe them. Now, in terms of the formation mechanism, again, from theoretical studies, the expectation has been that binary black holes can form in 2 main different ways, physically very different ways. One is through isolated binaries, 2 regular stars, massive, one going around the other, eventually forming 2 black holes. If your system doesn't get disrupted, then you might get a merging black hole at the end. And theoretical models exist for forming these at low metallicity, like we need for the system, all the way down to 0 metallicity, or also involving rapid rotation. For dense clusters, theoretical predictions exist for formation in old globular clusters, in young clusters, but also in galactic centers as well, where you have high stellar densities. This is a slide that basically summarizes almost all of the literature, not just the critical ones. And of course, I won't go into any detail, but I want to highlight one item. The very first prediction and quantitative analysis of binary black holes, it goes back to 1997, although there is an older paper, even before the discovery of the Hulse-Taylor pulsar, that predicted or discussed the existence of binary black holes back in the 70s. But quantitative predictions started in the late 90s. But all of these predictions never accounted for low metallicity because we were looking at our own galaxy mainly. And only at about 2010, starting with Belczynski et al., predictions for heavy black holes like the ones we have now observed have been produced through theoretical modeling. So these post-2010 models are basically able to produce these massive black holes because we understood in astronomy, royal we, that stellar winds of massive stars are not as strong as we thought in previous years. And also, if you account for lower metallicity, then that can give you massive black holes as we observe them. In terms of how isolated binaries evolve to give you binary black holes, where it's a complex process, and I won't go into the detail. The slide is just to scare you and realize that there's a lot of evolutionary stages a binary has to go through. And the punchline is that the modern simulations of this kind of process predict black hole masses and black hole rates consistent with the observations. Staying still in isolated binaries, you can avoid all this complex binary evolution with interactions and mass transfer if your stars are very rapidly rotating, relatively close to the breakup limit, and they become homogeneous, chemically homogeneous. And then again, there are recent theoretical studies in this area that give you masses and rates consistent with the discovery. Similar slide for the dynamics processes. This area of research has experienced great improvement since the 90s again, where only point mass, pure black hole dynamics was taken into account. Later, binary evolution was accounted a little more carefully, but the dynamics were kind of Mickey Mouse. And then from 2010, really we have been able computationally, different groups, to probe both the dynamics and the binary evolution involved. And we get also similar simulations and predictions for galactic centers and young star clusters. And again, another slide just to scare you. When it comes to how two black holes that will eventually merge can form in a cluster, you can form individual black holes early on from single stars, and then those black holes live through many, many, many dynamical interactions. Two major paths have been identified in the recent literature, and you can get something similar to what we observe, again, masses and rates consistent with this one discovery. So obviously, from an astrophysics point of view, one main question is how can we distinguish between these two different paths? I'll point out a couple of ways. Potentially through mass ratios, because the different models predict either comparable mass ratios, or in the dynamics you can get unequal mass ratios of the black holes. Spin orientations, if we can get to measure in detail spin tilts, which we are not able to do with this one discovery. And eventually, when we have larger samples, if we can track the rate as a function of redshift, then that can distinguish between the two formation models. So looking into the future, as I run out of time, I'll just make a few points. One is that as we progress from where we are now, the yellow curve, in terms of how far away we can see binary black hole mergers of different total mass, we will eventually be reaching cosmological distances, and that certainly will be of interest. In terms of rate expectations, I can imagine you might be discovering, if you have reported one, what's going on with the rest of your data. Well, I'm sitting in front of the lab director and the spokeswoman. I'm not about to tell you anything. But we hope to be able to put tight constraints on the rate. And using our analysis so far, we can predict that even if we scale everything to the 16 coincident days of data we have, and we scale everything to what we have seen so far, then the probability that by the end of our first observing run, which ended in January, the probability of getting more than 0 events reaches about 90%. And then as we improve our sensitivity, if our second observing run, for example, is close to its highest sensitivity, as the first observing run was, then the probability of getting more than 5 sources just in that run becomes 100%. And you can see how things progress with additional runs. Ultimately, we'd like to probe the black hole mass distribution and also derive quantitative constraints for the rates and hence understand the astrophysics. Now, there's more to look forward to. Of course, these are only binary black holes. Of course, what we do anticipate is neutron star systems, hence the connection with my Bethe prize, which I promised I'll make. We are in this range in terms of expectations for rates, so we are hopeful, obviously. And then we hope to have tighter either upper limits for these neutron stars or rate predictions, measurements, mass and spin distribution, electromagnetic counterparts, potentially spanning the full range from gamma rays down to radio, identifying host galaxies, maybe a new way of measuring H0, and of course, we'll be very happy to go to neutron star equation of state constraints. I'm past my time. I can see I'm conveniently short that I don't see the clock unless I do this. But I do want to also mention, there was a question earlier, that there's a lot more things to, of course, look forward to with LIGO science. Stochastic background, maybe from these binary black holes, that should be a lot more of them at large distances, but also a supernova maybe close by, and maybe pulsars are emitting gravitational wave emission. Now, looking into space developments and gravitational wave detection in space, I'll just say this is again a complex plot. I'll just tell you the one thing, that there is, with this one source and in the implied rate associated with this source, there is a good chance that about thousands of binary black holes that can be seen by LISA whenever LISA is built. And of these, hundreds would be such that they will be seen in LISA and then also be seen within LIGO. So I can imagine that would be an amazing opportunity to have for black hole studies. Also, binary black holes in clusters are expected to be eccentric early on before they reach the LIGO band. So if we see eccentricity in LISA, then we can distinguish formation paths. And I'm going to leave you with this slide. We're very excited with what's coming. Gravitational wave astronomy, astrophysics, and physics is here. Thank you very much.
Thank you very much, Vicky. So a couple of questions. Everybody's running off to the, okay, yes.
You mentioned that one of the scientific conclusions was that these black holes were formed from low metallicity stars. How do you know that they weren't formed as smaller black holes that subsequently gained mass?
Because right now, our best theoretical understanding in dense environments is that when you form smaller black holes and they start interacting with one another, they're actually not merging. They tend to kick each black hole out of the dense clusters. And this could change, of course. These are our theoretical understanding always evolves, but right now it's not a expected formation path.
Thank you.
One more question?
This candidate event, this
yeah.
LVT,
yeah.
Is there any future work or analysis that's either planned or can be done which can determine one way or another if it's noise or if it's a real event? Or is it always going to just be inconclusive whether or not this was a real event?
The exact quantitative results will change a little bit when we analyze the full data chunk that we have for observing run number one. But overall, they won't change. It will not suddenly become from a 2 plus sigma detection. It will not become a 5 sigma. I'm sorry, a trigger. It will not become a 5 sigma detection.
Okay, so I think we're running out of time. So we'd like to thank again our speakers and APS.